As technology grows more compact, mechanical engineers are developing new kinds of mechanics for smaller devices.
We're moving to systems at smaller and smaller scales.
One field of research in this area is microelectrical mechanical systems, or MEMS. These are devices that are so small that they blur the distinction between a mechanical system and a microchip. MEMS brings mechanics down to the scale where many devices that were traditionally in the realm of electronics, such as the oscillators used for filtering noise in mobile phones, become replaced by MEMS systems, such as micromechanical resonators, which achieve the same end in a much smaller, more energy-efficient package, resulting in far more sophisticated electronics.
So MEMS allows you to tightly integrate computing, sensing, and actuation in a very small package with unprecedented level of integration across these three levels. One of the problems with MEMS devices is it's very hard to manipulate devices and assemble them at the micro level.
You cannot just take big things and shrink them down.
So we need to think about new ways to fabricate as well as to understand the behavior of systems as they get smaller and smaller.
Penn Engineering has a rich history in the field of robotics and is currently working on building robots that can navigate intelligently in the physical world and devices to help and augment humans. But Penn researchers are moving into combining the field of robotics with microsystems.
So one of the things that we're doing in our lab is we're building tools that will allow cell biologists to be able to manipulate single cells.
Current manipulations of nuclei and cells take a lot of time and effort, pretty much a hands-on job by a technician, and the yield is of the order of 1 in 1,000.
You can actually damage the cells when you're extracting them. So by getting a machine to automate it, you essentially have improved reliability, you have better speed, and you have less human involvement in the process. We're talking about a robot that has hand-eye coordination that far surpasses anything that a dexterous human could exhibit.
Meaning vast improvements in the efficiency of cell biology research. And while it might not seem it, this is the promise of research in Penn's mechanical engineering and applied mechanics.
Some might think if they look at the things that our students and the faculty in the department are involved in, they may think that this is not mechanical engineering as they've imagined it. Although the emphasis these days is evolving in new directions, the underlying principles are those that have been deeply rooted in mechanical engineering over, say, the last 100 years or more.
As mechanical engineering research evolves, Penn Engineering is uniquely positioned to cross boundaries into these emerging interdisciplinary fields.
I think we attract students who are interested in engineering beyond just a specific discipline, but also in the way these disciplines interact with other disciplines.
So the mechanical engineering student tends to have a combination of hands-on experience as well as a nature to think about things deeply and analytically.
Which is why mechanical engineering at Penn is about simulation and analysis as well as design and fabrication. With over 50 million people already infected, major steps are needed to combat the spread of the AIDS epidemic. Right now it takes several hours to perform an HIV test. Penn researchers are working on a way to create a much more efficient diagnostic.
The fast diagnostics is desirable to prevent an infected person from infecting others. Information is a very powerful tool.
Dr. Bao works in a field called Microfluidics. Using computer modeling and microfabrication, Penn researchers are studying the mechanics of fluid flows and suspensions inside of microchannels and how electrical and magnetic forces can be used to control these fluids. This will allow them to create microscopic devices that can cause chemical reaction. In other words, reproducing an entire chemistry lab on a microchip. In a regular laboratory, technicians are required to move samples from one device to another, but Microfluidics lab-on-a-chip technology automates this process in miniature, allowing tests to be very inexpensive and operated by untrained personnel. Penn is developing a microfluidics chip that would automatically detect the HIV virus from a small sample of oral fluid. This would allow a diagnosis to be obtained in minutes rather than hours. And at the cost of only a few dollars a test, this chip could become a powerful new tool in fighting the spread of this deadly disease.
There's other projects that our students do outside of the classroom that very much enrich their experience here at Penn.
These projects include the National Solar Car Competition, further projects in robotics, and independent research. But engineering experience at Penn goes beyond technology. New academic programs in business and engineering promise to enrich Penn engineers further.
The engineering entrepreneurship track is based on the premise that engineers create great companies. Engineers like to create devices, but customers like to buy products. You've got an initial idea, and then how to develop that idea, into a market viable product. How to then gather your resources, to actually create a company, and then what your leadership role is in that company.
While the curriculum ensures strong fundamentals, these kinds of programs make Penn engineers better rounded, free-thinking, and innovative.
Nanotechnology is the design and fabrication of systems that are extremely small, on the order of 10,000, 50,000 times smaller than a human hair. When you are reaching that length scale, the atoms and the individual molecules start to become important.
Penn engineers have a rich tradition in designing and analyzing the mechanics of materials. Dr. Lucas is attempting to create nanocomposite materials that would be a fundamental improvement on the molecular structure of natural materials.
The drawback of building things with what nature gives us is that there are a very limited set of physical properties that we can have.
For example, in electronic devices, components are set into an insulating plastic board, which is inlaid with a conductor that connects these components to each other. This board needs to be electrically insulating, but for this reason, it is also extremely bad at dissipating the heat generated by the device. This has become a major hurdle in making faster, smaller computers.
What you want is something that's very highly thermally conductive and has a very low electrical conductivity. The work that I'm interested in doing is trying to design how materials are structured. How can you arrange the individual atoms and molecules in a structure? When one has the ability to control at an atomic scale or a molecular scale individual atoms and molecules, you can create from scratch materials that have the properties that you want,
allowing for a new generation of smaller, more powerful electronics.
It's very hard to compartmentalize engineering design, development, research into one department, and the education at Penn and the research at Penn reflects that.